Hello, everybody. My name is Yuzi Liu, and today I will be presenting about variation of calculus along with its applications. So I will split today's contents into two parts. On the first, I will talk about more about math, what is variation of calculus, and when we dealing with how do we deal with a variation of calculus problem. And the second part, I will talk about the application of variation of calculus in a real life. So we will explain how does the variation of calculus can be used into different fields such as finance, economics, or machine learning. AI is kind of popping now, so machine learning is also can use a tool of variation of calculus. So let's jump into our topics today. So firstly, I want to briefly talk about what is functional, since this is really important, really fundamental stuff, but kind of important. So functional and so what's the difference between functionals and functions? Because they look the same, but it doesn't mean they're exactly the same thing. So as we learned in high school, a function takes the individual values, for example, a number from a domain and output the other numbers into a codomain. So it's basically what function does is mapping a bunch of points, or it maps or domain into the range. So functional is a bit different, but it's still in the categories of functions. So functional takes a function as its input and produces a real number as its output. For example, we have functional J here. And as we can see, J is a functional which takes f y of x is a function to his input, and it will output a real number f of, we usually write this in L since we're setting up the Lagrange. So small changes right there. So as we can see here, y of x is a function, and j is a functional which maps the function to a real number by here we're integrating L, the big L, over a certain interval. Here we have AB. So when we think about taking a function as an input, I personally think about composite functions, since sometimes we write composite function in this way. Does it also mean the function g also the function g takes f of x as its input? So what's the difference between functionals and composite functions? Are they the same or they're different? So to figure out the question, we have to understand, well, what is a composite functions? So a composite function is more like a combination of functions. So where the output of one function become the input of another functions, but functional seems like doing the same thing, but functional is more dealing the function as a whole. So they operate on the function themselves and provide a way to evaluate and analyze the behavior of functions in relations to a certain criteria or objectives. So in conclusions, we see composite functions is not functionals, although they kind of all take a function as an input, but functional is more dealing function as a whole, unlike combination functions, only just a combination of two functions. And now here we come to our topics today, variation of calculus. So we recall in our course, our objective is just to find extremal values. And here we're doing the same thing, but unlike what we've learned before, here we're minimizing or maximizing a functional, not a functions. So our minimizer should be a function, not a point. So here we're dealing with the extremal problem is just going to be we minimize a functional subject to a constraint. The constraint will be given in questions. So we will also talk about it later on, and I will also introduce a really powerful tool. Here is called Euler-Lagrange equations. So once we have or we have to firstly set up a Lagrange functions, then we take partial derivative to the functions and this input, and we have to the equation always hold. So by solving the system of equations, we will have our final answers, which is u star of x, and this function is the optimized point, is the optimizer for our functionals. And here, and now we will look at some general questions about variation of calculus. So here we have our general question. So we will be asked to solve the optimizing problems. So in this case, we have to maximize or minimize our functional f. As we know, f is a functional which maps a function to a real numbers. And now here we have our constraint 2 points, u of a equals to a and u of b equals to b. And so to solve this question, we have to firstly set ux. We have to set a function like u of l of x. Let's just call it z and call this p. And this is basically equivalent to l of x ux u prime x, since we're setting z as u of x and p as u prime of x. So the purpose of doing this is later on we recall from our Euler-Lagrange equations. We need to, oops. We need to taking partial derivatives to x and to y. And notice here, y is not just a numbers or operators. It's more, y is a function, y of x. So by making y of x a equals to z, we're more easily to take derivatives. And once we have find the or new function L, and we can start to solve our questions. So now we have our function L, and we have to take a derivative to z, which is here, taking partials to the function, and minus and the dx times LP, and LP just representing taking the derivative responding to y prime here. And notice the Euler-Lagrange equation gave us a 0 as an answer. So this equation will always hold. Later on, through Euler-Lagrange equation, we will have an ODE, ordinary differential equations. We will just have to use the characteristic method to solve for the ODE, and we will eventually get an u star of x, and this one is our goal. This is going to be our extremer values. So this is basically the minimizer for the functionals. So let's take a look at an examples. So here comes to our first example. So our objective is to maximize the functional f from 0 to 1, and or functional is just or input value is u square of x plus u prime square of x. So, and subject to we have the boundary point right there. So we will later on use it to solve the ordinary differential equations. So follow the first step. We firstly have to set the Lagrange function L equals L of, just to make this clear, I will also write the input values here. Z and P. And here we're just simply replacing u of x to z and u prime of x to p. That is, and perhaps we just don't need this integral because we're just looking for functions. So here is our Lagrange functions right here. And now since we have to make this put this into the Euler-Lagrange equations, um, that is LZ. So consider the function L. We firstly have to find LZ. That is, and it's 2z, and notice z is just simply u of x. So this becomes 2ux. And now we have to find LP. To P, which is 2 u prime of x. And now we have or 1, 2, and we just simply have to put it into our Lagrange equations, and this will get us a ordinary differential equation. So here we have and to solve these questions, we firstly have to solve the partial part, which is we take the partial derivative respect to x first. This will give us so notice here u prime of x, if we're taking derivative respect to x, and this becomes 2 double prime of x equals to 0. And here we have an ODE equations and we need to solve. So remember the characteristic method is just we need to set up a function like notice here we're setting r equals u prime, r squared is just u prime double prime. Now we have this equals to 0, which is equivalent to r squared minus 1 is equal to 0. So now we have the roots 1 and -1. and these are not equivalent, which means we have a distinct roots. Therefore, u of x is c1 e x plus c2 e minus x. And since, let's add a page here. Since we already have this function, and we need to solve it subject to a constraint. Oops, not this one. So we will consider a system of equations. So here we have u of 0. I'll just directly have c1 plus c2 is equal to 1. c1e plus c2e minus 1 is equal to 1. And this will eventually get us the expression of c1 and c2. By solving this equation, we will have c1 equals to. So recall our function u of x is c1 equals to e plus 1 plus and equal. So this equation here is our optimal values for our functionals. So let's just go through this very quickly. So first of all, we have to identify the Lagrange functions, and we're taking partial derivative corresponding to z and p, and we're inputting the result into our Euler-Lagrange equations, and that will give us an ordinary differential equations. Now we have just solve it by the characteristic method, and by inputting our boundary point or constraint, we will solve for C1 and C2. Then eventually we'll have a minimizer. So U star of X is the minimizer for the functionals. So previously we talked about how to solve optimizing problem by using Euler Lagrange equations, and we've seen a specific example about how to finding extreme values, extreme functions subject to its functionals. And now you might wonder, oh, am I gonna ever use this in my life? Is it useful at all? The answer is apparently yes. So since I'm also majoring in economics, so I've took the course about maximizing about economics, which is all about maximizing profit, minimizing cost. So finding optimal values can be really useful. And yeah, let's jump into the topic. So the economical use of variation of calculus is it can bring a really big impact. So the calculus of variation and the Euler Lagrange equations, they're often employed in the models that examine how agents or customer firms or even the government, how do they make decisions over time, and We will build a model, and this model will typically involve maximizing some measures of utility, profit, even though social welfare, subject to or various constraints. For example, or budget constraints, how much money you have. Um, yeah, it's basically like that. So here we come to our first very useful case. Oops. That is consumption saving decisions. So how do we actually connect the optimizing functionals with economics? So here we have an answer. So remember in remember previously we talked about maximizing functional. Functional is always mapping a function to a real number. Um, that is a b f x I of x y prime of x. So how can we understand this? Like how do we put this into economical view? So for the interval, we can consider people's human lifetime as an interval, for example. Um, we're just gonna use this here. We considered our lifetime, for example, we can live from time A to time B, and how do we optimize my happiness subject to my wealth? Because in economics, we have a thing called utility functions. Utility function is basically uh, a quantitative method of how do you make your happiness into numbers, like quantify your happiness. For example, if we have the utility function u equals to uh, x1, x2 as good x1, x2, and AB is the quantity that I purchased them. So this function will give us a linear relationship between the good x1 and x2. So we can tell um, as we're buying more of x1, or utility function gets bigger. As we're purchasing more of good x2, where happiness decreases. So that's basically what utility function does. It's a way to measure your happiness into a number, because happiness is really hard to quantify. So that's in economics, we provide a way to sort of deal with it. Um, yeah, so consumption saving decisions basically talking about we will have to consider people's lifetime as an interval, and how do we minimize how do we maximize our happiness subject to or budget constraints. And also it can also comes to policy making. It is more of a macro view. So as we suppose a government wants to optimize the social welfare, which is a function of inflations and unemployment rate. Since if you have learned about economics, especially the macro part, you understand the government have various ways um, make to grow economy by social welfare, inflations, and unemployment rates. Um, so the government can control inflation by adjusting the interest rate. But there's a trade-off represented by the Phillips curve, which we will definitely talk about it later on. And the Euler-Lagrange equation can be used to find optimal path of the interest rate over time to maximize the social welfare. And so these two are basically the application part of various of calculus. So let's jump a bit more details about consumption saving decisions. So since we already talked about consumption saving decisions and policy making, how does this optimization method contribute to economics? So let's now interpret a little deeper about consumption saving decisions. So um so let's consider this case. Our purpose is to find, let's just say objective. Our objective is find optimal consumption. So consumption saving decision is basically we have to find the consumption path, which can here the consumption path is just or u of x. It's a function or u of c specifically because that's the consumption function. So our goal is to find the optimal path for individual over lifetimes and to maximize our utility. And usually the problem, let's do a little setup. So suppose individual wants to maximize their present value of their lifetime utility from the consumption of a function c of t. And notice that the individual has the initial wealth of W0. And the initial wealth can earn an interest with that's R on the savings. So we assume this person live from 0 to T. So that's the maximum, that's the life expectancy that he can get from 0 to T. Now we assume the interest rate and the rate of time change preference is constant. So just to make things a little bit easier because the real world is really complex. So we are trying to make the best approach as possible. So here we fix interest rate. So our utility function just going to be Coble-Douglas. It is a most common utility functions, and it is most representative utility functions that you can have in economics. I'll give you examples. So, our utility function is given by UC equals. So, it is a decrease. The second derivative is decreasing. So, as we can see here, for example, if you haven't ate anything for the whole day, and the first piece of pizza you get can maximize can bring you, let's say, 100 points of joy, and the second pizza you eat perhaps 90 because you're not that hungry, and after you eat like 10 pizzas, your the happiness that a pizza can give you is probably just 10. So it's decreasing, just like Coble-Douglas functions. So that's what humans' perspective or how do human measure utility over consumptions. So it's the most representative ones. So here we have a utility function as Cobb-Douglas is given by this. And the functional that we have to maximize is just simply integral 0 to t, the life expectancy, and E rho t ct dt. And we notice that rho is the rate of change preference over time. So since we're making a simple model, so we consider rho as a constant. So rho belongs to R is a constant. And also we have a constraint is it's gonna be our wealth or wealth change speed, rate of wealth change, and RW minus C. So this is all the monies that you can spend through your whole life. So now we have a functional. We also have a constraints, and now we need to find the functions to maximize the utility, this person's utilities. And so usually in economic test, the constraint function will be given specifically, but this time we just gonna give a general hint about how this method works in economics. So we're not gonna solve the whole thing, but we just I just wanted to give you guys an interpretations about how and why this optimization method can be used into economic field. So we just have to solve, so it's more like a math part. We just have to solve Euler-Lagrange equation. And when we apply, remember the Euler-Lagrange equation is the partials is was LZ. So it was this, and we're taking derivative corresponding to the functions first. That is and we also have to find C prime, which is 0 in this case. And we already have these two. And we plug it into the Lagrange equation, and it will give us an ODE. And later on, we will just have to solve for the ODEs. I think since this is a general case, it has the solutions, and eventually we'll get lambda is equal to 0.5 e rho t c 0.5. So this is what we will eventually get, and we would use it to solve for the minimizer. So to interpret this a little bit more about rho is that from this function we can see if rho is very high, a high rho means the individual is impatient, then the lambda will be higher, which leading to the higher consumption now rather than later. And also the Cobb-Douglas function form of the utility function means that the utility diminishing return to scales. So as our consumption increases, the marginal benefits. So that's called the marginal utility of consumption decreases. So this functions or this model explained a decision makings over a lifetime for individuals when we have limited budget constraints. How do we maximize the profit? How do we maximize the utilities as we can get? So therefore, that's for the consumption saving decisions. It's really useful because as an individuals, you don't know how under limited money you can spend. You wanted to maximize your joys as more as possible. So this consumption saving decision models sort of can give you a spending function, a consumption functions, which can maximize your utilities. Notice that um, the functional takes function as an input. So that's why it fits in this case very well. So we already finished consumption saving decisions, and now this case is more like a micro case. So it talks about individuals, and now we have to talk about something macro, which is policy makings. As we know, government also make a lot of policies. It's all based on economical models to to make um, to make human live better, to make our economy grow greater, bigger. So policy making is also a big term. So so in the policy making terms, um, we'll so I will provide the example which will focus on the monetary policies, where the central bank aims to stabilize the economy by minimizing the fluctuations, both inflations and output. So let's do a little setup here so we can understand this scenario a bit better. So we assume the central bank wants to minimize the deviations of an inflation pi of t. Since it's related to time, so the parameter is going to be t representing time from a target I star and output a y of t from its potential y star. Uh, the, the period is just gonna say 0 to t. So if we recall second year mathematics or statistic, we have a loss function which was given by, in this case, so we have to calculate the loss function. So this is our loss functions. It can also be used as or Lagrange equations right here. So now we have a Lagrange equations, and we just need to turn this into a functionals. And since we're making the monetary policies, we have to make our function subject to the Phillips curve. And notice that the Phillips curve is given by pi of t and alpha and beta are just the coefficients, the scale parameters here. And lambda is the weight given to the output stabilization relative to the inflation stabilizations. And now we have our functional. And also our constraint. Notice that the function that we want to minimize is a functional where we take pi of t as an input. And also we have constraints right there. Now we just have to solve, use the old way. We just have to solve by plugging into the Euler-Lagrange equations. So we will take a look at no, actually we're taking y. It's too long. So as we are having these two functions, we re-put it into the Euler equations, then we can solve for the optimum control yields, y of t. And this is our goal. Yeah, again, like I said, since it's a general models, I did not put the significant value into it. By going through these, setting up models is just to want to give a general guide of how this optimization method fits into the economy. So now we will have a function of y, and we will also get a optimal pi of t, which makes the minimized deviation as possible. So when we have these two functions, it's dependent on several variables, for example, alpha and beta. So so the parameter alpha and beta is the Phillips curve captures the aspect of the economic environment. For example, how responsive inflation is to changes in output, and the different economy conditions could lead to different optimal policies. So while we have our optimizer right here, we will have a function related on alpha and beta, and also lambda. And lambda is just the weight reflects on the central bank's preference. A higher lambda indicates that central bank is more concerned with stabilizing output than the inflations. So we will have these related to alpha, beta, and lambda. And also here we have also have mu, which is like a policy trade-off parameters. The Lagrange multiplier mu give us an insight of the trade-offs to the central bank faces. A high mu indicates that it's sticking close to the Phillips curve is particularly important. So we will have once we have the optimizer, we will have these four factors, which will be really key to government for the government to determine what policies to make what's the best possible policy that we can have to make economic growth. So yeah, in practical, the models can be really, really complicated. And since here we're just only giving application a clue of how the variation of calculus can fit into the economic models and benefit our world. So yeah, that's basically all we have today's. How do we find optimal values to a functional, where a functional is like a mapping which takes function as an input. That will be all. That's all contents for today. And thank you for listening, and have a nice year.